developed in partnership with Neo4j. In this course, you design a multi-agent system that transforms your structured and unstructured data into a knowledge graph. I found knowledge graphs really useful for high-stakes applications where accuracy of the information we store and retrieve is important. This course will teach you why and also give you a great set of tools for building these knowledge graphs. I'm delighted the instructor for this course is Andres Colliger, who is a developer evangelist for generative AI at Neo4j.
Thanks, Andrew. I'm excited to be back here to work with you on this course.
Similar to RAG, a knowledge graph system splits your text documents into chunks and stores them in a vector database. But in addition to that, it places the chunks into a graph structure, where each chunk is linked to entities extracted from the chunks. For example, a text chunk from a product review can contain entities such as product orders or delivery issues or product defects. To build a knowledge graph, you extract the relevant entities from the chunks, then connect the chunks and the entities in a graph through edges. Here, each edge represents a relationship. For example, maybe it represents that this chunk mentioned a certain product or that that product has an issue. The entities are retrieved alongside the relevant chunks to provide more relevant context to the LLM to generate more precise and accurate answers. You can also connect this type of graph to another graph containing additional information extracted from structured data, such as CSV files. In this course, Andres will walk you through how to build a multi-agent system that helps you do all this work of constructing this type of knowledge graph.
To transform your structured and unstructured data into a knowledge graph, you first need to decide on the graph schema, meaning what types of entities or nodes you can extract from the data and what relationships exist between them. Once you have the schema defined, you can construct the actual graph and store it in a graph database. Instead of manually looking at your data to find the graph schema, you will design a multi-agent system for doing that using Google's ADK, or Agent Development Kit. After you learn the basic syntax with ADK, you'll design your system one agent at a time. The first agent will converse with you to extract the goal and the type of graph you want to build. Then, given that goal, a group of agents will specialize in extracting the entities and relationships from your structured data, and another group of agents will handle your unstructured data. Finally, the final set of agents will connect the two models and construct the graph accordingly.
Many people have worked to create this course. I'd like to thank from Neo4j, Martin O'Hanlon and Adam Cowley. From deeplearning.ai, Christopher Policastro and Hara Salami also contributed to this course. In the first lesson, you learn more about the underlying structure of knowledge graphs and how you can build one and use it to identify root causes of product issues.
Sounds great. Let's get started. Go through what a knowledge graph means and how they help represent and retrieve relationships from your data. You'll then explore the data set you'll work on to build a knowledge graph. Let's dive in. So what is a knowledge graph? We're going to take a step back for a moment and reflect on relational databases and what a relational schema looks like. We all probably are familiar with some scenario like this, where there'll be some table on the left and some table on the right, and this table in the middle that is the join table that allows for multiple connections between the persons and the products in this particular example. So let's think about these two tables with the join table. If you ask a question like, what products has this person purchased? You'd first start with the person table and select this person here. It's identified by ABK. And of course, you do a join over to the person product table. And you'd see that the person product table has a join between the ABK and some chair, ABK and a lamp, ABK and a desk. Fantastic. One more join across from the person to the person product to the product table. Now you've got a complete answer where from ABK, you can see that here's the products that ABK has purchased, this chair, lamp, and a desk, and you can get the details about those purchases. What if you extended that question and you asked who else bought products that ABK bought? Well, you start with the same joins going from ABK to the products, and then you would join back to the person product table, and from there back to the person table, and now you would get this person EE, who has bought some products that ABK also bought. But notice that EE has also bought one extra product. That's interesting. So we could probably extend this one more step and ask, well, what product should we recommend that ABK buy next? Now, this is kind of the basics of doing a recommendation query. If you've got some purchase pattern from ABK that matches a purchase pattern from some other person or other group of people, the thing you want to recommend to ABK is what that other group of people bought that ABK has not. So the same joins apply from ABK through to the products, back to the other people that have bought those products. There's too many joins. It's getting a little confusing. There's actually a nicer way to actually think about this and to query this. Let's turn this into a graph. The first step is to just drop all the records that don't matter. All those gray records that weren't part of the original query, let's put those aside for the moment and focus on the records that we know about that are part of the data set so far that matters for this query about recommending something to ABK. Get rid of all the join table records in the middle, turn those into arrows connecting ABK directly over to the products that he's purchased, and the same thing for EE over to the products that they have purchased. And now just rearrange the records a little bit. So you've got ABK on one side, EE on the other side. And now it looks much nicer. It's much easier to understand what's going on. Both ABK and EE are connected to these products in the middle. But then also, this person EE is connected to another product that has no connection to ABK. You can start to turn this into a query by rephrasing it as a pattern match. Starting with ABK on the left side, you can describe a query in a query language called Cypher, where it looks a little bit like SQL if SQL had pattern matching abilities. So here we're going to describe a pattern that describes the data records that you want to find. We're going to match from the data record that we're going to call ABK that has a label of person and that has a property with the name key where the value of it is ABK. So that's in round parentheses. We know that that's a node in graph terms. And then we kind of have this right-facing arrow with colon purchased in there. That's a relationship type that is the purchased. So match a pattern where ABK purchased over to some other parentheses that we're going to call ABK products. That's going to be a pattern match from ABK to the products that ABK matched. We can return those directly, and that's going to be the products in the middle there. We can extend that pattern to include the other people who bought those products. Since we went from ABK to the products that ABK purchased, we can also have relationships going in to those products and say, okay, there's some other people who bought those products. This pattern will find all of the products that people have in common with ABK. We can extend it a little bit more to ask that recommendation question problem, where instead of saying that we just want to find these other products, the other products have a unique property where they're actually something that ABK does not have. So we have the same pattern match from ABK to some products to some other people, and then extend that to other products. And now we include a predicate saying we actually want a negative pattern to be true, that ABK has not purchased those other products. So where not ABK purchased those other products. So down there on the bottom, that dotted line from ABK to the couch, we want that to not exist. Now we're describing a pattern that both has records that should exist, something that should not exist. The other products now will be reduced to only products that ABK has not purchased. That's what we're going to use as a recommendation that he buy. So what really is a knowledge graph? It's a kind of database that represents information as nodes, representing things like people, products, blogs, whatever you might want to have as records in a database. But then also relationships that aren't simply a convention of using a join table, but that are first-class citizen. They're actually data records inside of the database that have a semantic meaning. They actually represent how two nodes are connected, and they add information about those two nodes. So both the nodes and relationships have key value properties. They have multiple labels on nodes. Relationships always have a direction, and they have a single type. And the query language that you use for doing pattern matching is called Cypher. And it turns out that this is super nice for mapping to natural language and really convenient for working with GenAI and LLMs, because LLMs are really good at natural language. If we go back for a moment here and just look at that query at the top, you can read that out loud and make sense of it. Match ABK, who's a person whose name is ABK, that bought some products that some other people have bought. They've bought some other products where ABK has not purchased those other products. The other thing that's interesting about knowledge graphs is that they're really convenient for combining unstructured data along with that structured data, whether that was some products that we have or people, whatever it might be in structured data. You can then add any kind of chunked text, do a vector representation of that, store that in the database as well, and combine both vector similarity search and pattern matching together for all kinds of powerful access patterns. So for example, if you want to do root cause analysis, And you imagine that you're a furniture manufacturer looking to understand customer complaints about your products. So you turn to your team of experts, data engineering, data analysis team, and say, hey, could you do some root cause analysis? I've heard a lot of complaints out on the internet about our products. Let's try to figure out what's going on. So the root cause analysis would include questions like which products have the most issues, and then based on those products, well, what part of the product is the actual problem? And then you might want to ask a question like, is there a problem with the part itself? Perhaps there are other things that are going on. People just don't like the product. But if you can take corrective measures, it would be because there's something either in the manufacturing process. What you're looking for here is for corrective measures that you can take. Do root cause analysis for something you can improve. So if it's a design problem, you could turn that over to the design team. They could take a look at what people's complaints are about. But if it's a manufacturing problem or a problem with a part somewhere, you can do some analysis on that, find the part problem, and either swap out the part for a new one or figure out how to improve the process itself. So as a data engineer, if you were handed this task, you would start with the usual thing. Ask some clarifying questions. Why are we really doing this? You want to be able to understand that there's possible manufacturing problems in the supply chain. Cool, okay. Second question is, or if that's what we want to find out, what data is available that we can do this analysis with? So it turns out in this scenario, we've got a bill of materials, some CSV files that connect the product all the way to the suppliers from those products. Maybe it came from some spreadsheets, maybe it came from some relational database that isn't really suited for doing analysis. That's okay too. And you also have some data from user reviews that you scraped from some websites on the internet. You want to be able to combine those into one data set that you can then do some analysis on. So to do that analysis, you're going to build a knowledge graph that connects all the data. So here's what the target data model is going to look like. On the left, in the sort of beige boxes over there, you see the CSV files that are available. Each one of those is going to turn into nodes in the graph or relationships in the graph. That's going to be the kind of what we're going to call the domain graph. On the right-hand side, on the bottom there, you also see some beige boxes that represents markdown files. Those markdown files are going to be chunked up. They're going to create some documents inside of the graph as well. And then all of this is going to get connected. We'll look at some of the details as we actually go through doing the agent descriptions themselves. But what I want to call out here for you right now is that these are really very connected, but also very distinct parts of the graph. We've got the data sources, the structured data on the one side there. That's going to turn into what we call the domain graph. So that's the structured data that we know that we can query with pattern matching. On the other side, the unstructured data sources are not going to be queried in the same way, and they're not going to be imported in the same way either. So they're going to turn into what we call the lexical graph, which represents the original textual data, plus also the structure around that textual data. To connect those two pieces, the unstructured data and the structured data, we've got this part in the middle that we're going to call the subject graph. The subject graph is going to be subjects or entities that we pull out of the chunks. So the chunks will have some text, they'll be talking about products, maybe they'll be usernames and things. All of those things might be entities. We're going to find those, call those things subjects. And those subjects are going to be connected to objects. So the subjects talk about something. So some user, let's say that it's me, user ABK, loves this table. And so there'll be a subject predicate object in the subject graph that talks about ABK loving some table. That also, because ABK loves a table, the table can correspond with the product that we have in the structured data. If ABK mentions a table, and the table is a product that exists in the structured data, we can then connect the entities that we've extracted from the text all the way over to the structured data that we've got in from the CSV files. Don't worry, we're going to do this step by step. On a high level, this is what you're going to end up with: a graph with subgraphs within it, a domain graph, a subject graph, and a lexical graph. The goal of the knowledge graph you'll build, let's go through the details of the multi-agent system you'll design to first find the graph model and then construct the graph. There are lots of definitions for an agent. Here's my definition. I like to think about agents from an engineering perspective, and for me, it's a fancy new kind of control flow operator. Basically, you have a loop, and inside of the loop, there's a call to an LLM that then figures out what it wants to do, and then based on what it wants to do, passes that back over to the computer side, to the client side, and really runs into a switch statement that performs potential actions. So in this loop, this is really just intelligent behavior that's happening because of the LLM call, but the execution of that intelligent behavior is still happening through code. What's great about this architecture, of course, is that agents are really powerful because you've got an LLM there to do some reasoning and call out to tools that can do anything you can do with code. And it's adaptive because the LLM is given memory, so it can learn what's happened either through the conversation or through things that you've saved into memory that are important for it to decide future outcomes. And it's pretty easy to get started because you're really just doing natural language descriptions through the prompts about what the agent should do. But all this power and ease comes with some downsides. It can be slow working with an agent because the calls out to a remote LLM is a bit expensive and slow. It's also non-deterministic, well, because LLMs are non-deterministic. And, token cost over time can really add up quite a lot. So if you're running an agent over time in production for thousands and thousands of calls, the token cost gets really expensive really quickly. That's one of the advantages of moving to a multi-agent system, is that you can actually improve some of the downsides here. So what is exactly a multi-agent system? It is, of course, just a system where you have multiple agents working collaboratively on a single goal. The agents typically are arranged into a kind of a hierarchy where you have a top-level agent that manages the overall flow, and then as many sub-level agents as you'd like to that have either different phases of the work or very specific tasks that they're performing. The agents interact in a couple different ways. There's a main conversational thread that's basically happening with the user, where the user might have some message that they kick off the work with. And then each of the agents can decide, is this work that I can do or something that somebody else should do? So can I delegate this to a different agent? So you can see in this illustration here that the root agent is able to delegate to either agent A or agent B. Internally, agent A and agent B can do some work using the tools that they've been given. One of the tools in agent B is unique. This P agent here, this P function, is actually going to be an agent itself, but being called as if it were a tool. So there's two ways for tools to interact, either agents delegating to each other or an agent that's behaving as a tool being called by another agent. And along the way, you've got specific checkpoints with the user that are possible whenever you have any of these transitions. So what is the multi-agent system that you'll build? You'll build parts of a knowledge graph agent, focusing on the sub-agents that perform knowledge graph construction. You'll learn the basics of building an agent using Google's ADK. You'll learn what memory is and how to use it for recording critical information. You'll define some tools. And of course, all of this will converge from open-ended conversation to executable code. This beautiful diagram are all the agents and the flow of agents and their interactions. Let's walk through this a little bit at a time. At the top level, this is the agent that manages the overall introduction of the user to what's possible, what the agent's responsibility is, and helping the user understand what's the workflow that's possible here, from the knowledge graph construction all the way to doing graph retrieval. So this is really a conversational agent that itself is not going to do any work, but it's going to guide the user through the different phases of work that are going to occur. It's this next level of agents down that are really going to manage the individual workflows. And there are three major workflows. Really on the left, we've got two workflows, the structured data agent and the unstructured data agent. These are responsible for taking the user through the idea of what they might want to do, all the way to constructing a graph. And then, if those have done their job, this third agent, the graph rag agent on the right side, is responsible for helping the user actually answer questions using that graph. Both the structured data agent and the unstructured data agent are workflow agents. They perform their work by interacting with the user and helping them go through the steps of what needs to happen from the idea of what they want to do all the way to describing the graph. And they do that by delegating to sub-agents that specialize in each phase of the workflow. You'll see some replication here that both the structured and unstructured data have some agents that are in common, and I'll touch on those as we get into the one level down. Okay, so here's the sub-agents that are actually doing the workflow for structured data. Let's walk through these one at a time. And also what's important to note here is the output of actually these agents doing their work. If you think about yourself as being a data engineer that's been given the task of actually performing this work, each of these agents are kind of what you would do yourself if you're engaging in the work. This first one, the user intent agent, is what you would do when you've been asked to do some task for data analysis. And whoever asked that, you respond to with some questions. Hey, could you clarify what you want me to do? Give me, what are the goals you're after? What kind of analysis do you want me to perform? And it's really important to nail that down up front. This is the kind of the requirements or the direction overall of what the job is. So this user intent agent, even though it's collaborative and kind of conversational, the output of this is really important. We're capturing what is the user goal and what are they trying to get out of this work. Based on that user goal then, this next agent down, the file suggestion agent, is going to take into account what has been established through the user intent agent as the direction and the goal of what the work is. And then it's going to look at the data files that are available and try to find from those data files which ones are useful for actually achieving that goal. There might be more files that are available. There might be even multiple data sources that are available. Here we're simplifying it down to just making suggestions for files that are available on disk. The output of that ends up being a list of suggested files that have been approved by the user, and then that gets input into the next agent, which is the schema proposal agent. The schema proposal agent is actually a pair of agents formed in a critic pattern, where one of the agents is responsible for making a proposal about what the schema could look like, and the next one is going to be a critic saying, well, maybe that's not quite so right, think about changing it in this way or that way. We'll look at the details in a later lesson. But the idea here is that this pairing of agents internally will loop through what's possible, self-criticize itself, and the outcome of that should be a good graph schema that uses the files that were approved from the previous agent and also in compliance with user goals that were set by the first agent, producing a graph schema that can answer questions that are useful for the user. So the output of all of that we're calling a graph construction plan. It's not a graph itself, but it's a description about how to construct that graph. The second workflow in the middle, the first two parts of that workflow are the exact same as the structured data workflow. Here in the middle, we're dealing with unstructured data, but it still begins with understanding what is the user intent for bringing in the unstructured data, and here that's markdown files. And then, okay, if you understand why the user wants to bring in some markdown files, you can identify which files are relevant. Again, a file suggestion agent would do that. Similar behavior to the structured data, but this third step is different. In the third step, rather than designing a schema based on some CSV files, all you have is text. And from that text, how do you create a graph? Well, the approach here is that we're going to have two specialized agents that look through the text and identify what are called entities, so people, places, and things that occur within the text. And also for those entities, it identifies what facts are describing those entities within the text. So let's say that it was I was in the text and I had some reviews of local coffee shops. It might reveal that, ABK really loves to source coffee from Phil's, because who doesn't? So those are facts that could be extracted from the text. The goal of this agent is actually to find out what kinds of facts can be extracted and not do the extraction, but simply describe what's possible. And so that we're going to be calling a knowledge extraction plan. The knowledge extraction plan paired with the graph construction plan from the structured data together give all the rules that we need using the graph construction plan and the graph extraction plan. This red box down in the corner then is just a single tool that has multiple tools internally that actually can take those plans and do the extraction itself and do the construction itself. It'll loop over all the construction rules to create a domain graph, loop over all the markdown files, chunk them up, do the vector embedding of those, and then also extract entities and the facts, and then connect those to the structured data. In lessons 4 through 8, you'll go through the entire workflow for structured data, from user intent, file suggestions, to the schema proposal. Then, we'll skip over to the unstructured data, just the entity and fact type proposal. And then finally, we'll look at the particular tool in lesson 8 that does the graph construction itself. It does all the hard work that the previous agents really did the reasoning about what the work should be. In the next lesson, we'll actually get into doing some coding, building your first agent. We're going to be using Google's ADK. If you're already familiar with Google ADK, you could skip over that lesson and move on to actually building the multi-agent system. But I think it's a really good overview, and also it helps you understand how I think about it and how I've implemented it in this particular multi-agent system. So it's nice to walk through. I'll see you there. To build the multi-agent system, you'll use Google's ADK, or Agent Development Kit, which is a framework for developing agents. In this lesson, you'll learn how to create and run one agent as well as a team of agents. All right, let's go. In this lesson, you'll familiarize yourself with Google's Agent Development Kit, and you'll use that for building agents throughout this multi-agent system. In this lesson, you'll learn how to create and run an agent using ADK, and the imports that we're doing here, of course, the standard OS, and then a bunch of stuff from Google ADK itself. We're going to import this agent, which is going to be the key thing for actually describing what an agent is. For interacting with an LLM, we're going to be using the Light LLM library, so we're going to import that here. And this is a little wrapper for letting Google ADK talk to OpenAI. And then we're also going to need some memory for the agent. For the memory, we're going to use the memory session service. And then finally, the agent also needs a way to run, so we're going to import a runner. We also have some typing stuff here that's not really so important for how all this works. Let's go ahead and make sure that all that imports. Great, all the libraries are imported. So the next part then is to start defining the models that we're going to use. We're going to be using OpenAI for this course. So let's go ahead and import, we'll define what the model is going to be itself is OpenAI's GPT-4o. Again, we're going to be using Light LLM for actually reaching out to the OpenAI API. And we're just going to go ahead and try a sample execution of completing a chat with that. So if you look at the chat here, you'll notice that we're just setting up a message that we're going to send to OpenAI. And we're going to ask it the question, are you ready? So if that all works successfully, we'll get a good message from OpenAI letting us know that this works. Looking at the model of response, there's a lot of information here, but the key part is that the response includes a message from OpenAI saying, yes, I'm ready. How can I assist you today? OpenAI is all set to go. We're also using Neo4j today, so we're going to import a helper library that combines Neo4j with Google ADK in a nice way. And that library is something we can take a look at to see the details of what's going on. The import that we're going to use is just from Neo4j for ADK, import the GraphDB library. Let's take a look at those details. Okay, now we're inside of Neo4j for ADK, and you can see it starts off pretty simply. We import some stuff from the operating system. We, of course, load up the environment. And then from Neo4j, the Python package, we load up the graph database, and you also get a result class definition. Now, a bunch of these functions that are in here are just really nice for just wrapping up how to interact with Neo4j and presenting the results from Neo4j in a way that Google ADK likes to see things. One of the key things is that results should come back either as a dictionary with a status that is a success or a status that is an error. These two helper functions help do that. You can call tool success or tool error along with some extra arguments and actually get a nicely formatted result from any kind of call. To that, we then go ahead and also integrate a helper library. Results that are handled by Google ADK need to be easily persisted. So this function call here to Python basically goes through all the different kinds of results you can get back from Neo4j and makes them easily serializable in a nice format for Google ADK. You can look at the details if you want to see what's going on here. The key part, of course, is this function that takes the Neo4j result, here passed in as just a result, basically calls that to Python package, packages all that up into a result that is easily used by Google ADK. Each of those helper functions is then also used by this upper level class called Neo4j for ADK. And this is really a wrapper that combines a Neo4j driver, initializes the environment variables used there, allows access to the driver, and then has a special function here for sending queries. And it'll send any kind of query you'd like to, but then uses those helper functions for actually reformatting those results into a nice Google ADK result. At the end then, because we're just going to have one driver and one connection that we're using, we're going to have a singleton of this class that we use. This is the GraphDB that we're going to actually expose as a variable and use that through all the notebooks. Okay, we took a look at Neo4j for ADK. Let's continue with the notebook. So now we've got everything set up and we can start to define an agent itself. Okay, with our Neo4j wrapper ready, let's go ahead and give it a try. You can just send any kind of Neo4j query that you'd like to, as long as it's valid cipher. Here, the cipher that we're sending is a very simple cipher statement that doesn't do any work other than directly return a result. Here, the result is a string, Neo4j is ready, passing that back aliased as a message variable. So if we run this and then print the results, you'll see that it's been packaged up into this nice little dictionary with a status success and then the query result containing an array of all the rows returned from the database. Great, with OpenAI ready and Neo4j ready, we can start to define our tools themselves and the agent eventually. Tool definition is an important part in actually defining an agent. Without tools, an agent can do a lot of thinking, maybe have some chats, but it can't really do any interactions with the environment or with the world around it. So we're going to define a very simple tool just to kind of illustrate what kind of things an agent can do. Hello World is the classic, of course. So we're going to develop the Hello World version for an agent's tool, and we're going to call it Say Hello. So tools can be simply defined as functions. Here the function is just say hello. It takes a single argument, person name as a string, and it returns a dictionary. Of course, that dictionary is the Google ADK dictionary that likes to see all results in. And it also has a couple important parts here. There's a doc string that's here, which is always nice when you're writing code. It's also especially critical when you're developing tools for Google ADK. This doc string is what lets Google ADK understand what actually this tool does. This gets passed along to the LLM when the LLM is told, here's all the tools that are available, and also here's what those tools are described as doing. So there's a couple of important parts that we should go through here. You describe what the tool does. Here it just formats a welcome message to a named person, of course, passed in as person name. You describe the arguments that are being passed in, and also the result. The result here is consistent through all of the tools because the result is a dictionary that Google ADK likes to see. But you can add a little extra detail if you want to here. For instance, if you know the kinds of errors that might come back, you could explain that here as well. Inside, the function is incredibly simple. All we're doing is using Neo4j again to actually do a hello world. We're going to call out to Neo4j, sending a query where we're still going to return a hello to you, but then we're also going to concatenate that with this person name, which is passed in as an argument to the function. That's going to get passed in as a query parameter to this query. Whenever you see that $sign in a Neo4j cipher statement, that means here's a query parameter. So here in this array, in this dictionary that's being passed in, you'll see the person name is being passed in as person name. That'll get substituted in as this variable here, not as a template substitution, but as the value gets passed in. And then this whole query will get executed. So let's define that function. And of course, because this function is just a normal function, we can try to run it. So we can print saying hello to ABK and expect to see a very nice Google ADK formatted result that was successful, where the query result that was sent off to Neo4j has the reply, hello to you, ABK, doing that concatenation. Fantastic. Now, just a side note here about query parameters. Part of why we're doing that, this is good discipline for any kind of query language that we're using. Most query languages have the ability to have query parameters. And one of the reasons you do that is to avoid injection attacks, right? So that people can't pass in values that look like SQL statements or cipher statements or any other query language statement as a value and have that concatenated into a string. That can cause all kinds of mayhem. So instead, you pass in a query parameter. And here, for instance, if I pass in the name and say, actually, the name's going to be, hey, return some string here, this could be some malicious code instead that gets passed in as the person's name. If you just concatenated that as a string, all kinds of bad things can happen. Instead, because it's a query parameter, that still just behaves as a variable. It gets passed in, it gets concatenated as a string with the other string, and the result is simply a hello to the somewhat friendly and malicious injection attack. And of course, it's been avoided now. We have the basic tool available. Now we can define an agent that's going to use that tool. Now there are a couple of components of defining an agent. It's common across all frameworks. They all do some variations of the same idea. Let's take a look at what's happening inside of Google ADK to define an agent. Now, if you recall earlier, we had imported this agent class from Google ADK. So we're going to make an instance of that class, and it takes a bunch of parameters. So the first thing that's important is that every agent is given a name. Here, we're going to call it hello agent underscore v1. This is in case you have multiple versions of the agent that you want to have at the same time, or if you want to actually have different versioned instructions as well. Having an idea of what the version of this agent is very helpful for debugging later on. You also pass in the model that you want to use. Or if you recall, we defined LLM before as being a call through light LLM out to OpenAI. So we're going to use that here. And these next two are pretty critical for how the Google ADK actually orchestrates and executes agents. The first part is this description of the agent. This is a little bit like the docstring of the tool, what describes what does this agent do. This lets Google ADK and also the other agents understand what is the purpose of this agent, and is there occasions when I should call this agent rather than doing something myself, what's called agent delegation. So that's for other agents to know what to do with the agent here. Then for the agent itself, you provide some instruction. And the instruction is basically the same kind of thing you would have done with when you're doing prompt engineering and you're defining the system prompt for the LLM. This is the same kind of thing that you would do there. This is a hello world agent, so it is, of course, very helpful. It's a helpful assistant that's going to chat with the user, and it really only has one tool that it wants to use. So you describe that tool here so that the agent understands, not just from the tool definition, but also from your instructions that you're giving it, how to think about that tool and when to use that tool. So here, if the user provides their name, use the say hello tool to give them a custom greeting. And then the final part, of course, is we have to make those tools available. The tools get passed in as an array of just the function names themselves. So we're going to pass in say hello. And then the agent then has access to that tool. It knows what to do with that tool because we give it instructions, and other agents, if there are other agents, know what this agent's role is. Now that we have an agent and the agent has the tool and it has instructions about how to use that tool, now we need to run the agent. This is the final part in creating a very basic agentic system. An agent has to have an execution environment. So if you look at this diagram here, you'll see that inner box here. This is the execution environment that happens. There's a runner class that actually manages all the event loops, basically for calling out to the LLM, passing results from the LLM to particular agents, and coordinating all the agents themselves and how they execute. Each of those runners also has access to various services, whether that is in-memory services for like doing actual memory. Memory could be in-memory, or it could be, you could use a database like Neo4j for memory as well. So that gets you access to storage. Then there's the execution logic that inside of the execution loop, here are the steps for actually running things and coordinating the agent, whether agents are running in parallel or in sequence or in a loop. This all together actually is the execution environment for the agent. Okay. We're going to do this by hand first, and then show how we can wrap this up to a little convenience method. When you're doing your own development with Google ADK, Google ADK has really great tooling for just defining an agent and then using the tooling for actually just running that agent and providing it the full execution environment that it needs. We're going to be doing that by hand inside of the notebook, so let's do that one step at a time and then wrap it up into a little helper. So there are a couple of things you're going to need to actually set up the execution environment. Every runtime actually runs within a session. You could, of course, have multiple sessions that are running in some production environment. Here we're going to have a single session where we're going to go ahead and just set up the in-memory service, which provides context and state for the agent as it's running. We're going to create the session service based on that memory and also for the particular agent that we're writing. And also assuming that we have a user, we're going to assume that we have a single user, a single application that we're running, and a single session. All that is going to be used here in the create session to actually create a single executable state to actually be run. And then the runner is going to run that state given the agent that it has. So here the runner combines the agent that we want to run, our hello world agent. The app name is going to be the same as we passed into the session here. And also the session service is going to be the session within which this agent runs. Again, in a production environment, there might be multiple sessions, there might be multiple applications that are using this agent. That's why these are all different arguments to run. Okay, now there's a lot to walk through just to actually do the running of the agent as well. So let's go through this step by step and take our time. We know that we just have this runner available that we just defined, and we're going to do just a single loop through with a single user message and allow the runner to execute the agent reacting to that message from the user. So we're going to define a user message, and I'm simply going to say, hello, I'm ABK, and we'll go ahead and print that message out in a friendly way so we ourselves can see as this is running what's going on. That message that is just a string has to get packed up into a data structure that Google ADK, the runtime environment, expects. Usually this is handled behind the scenes for you, of course, but we're going to do this by hand. So we're going to create this content class here, and the role of the content that we're creating is from the user. This is a user message. Content can have multiple parts. So we're going to create an array of parts where one of the parts has some text, where the text is a user message. This is all bundled up to do more complex things. Here we're just trying to run a single message from a single user, but this gives you lots of flexibility when you have lots of extra things going on. And this is basically creating a content event that then has to get processed by the agent runtime system. Also, we're going to go ahead and set up a response from the agent system in case it doesn't do anything. So after you pass in a message, we're going to actually go through running that message and letting the agent get a chance to respond, but it's possible that the agent doesn't respond. There's this notion of having a final response, which is a flag that an agent can set in different ways to actually indicate, okay, I'm done thinking about this, or I'm done processing this, so you can go on and go back to the user. In case the agent does nothing, a final response may not get set. So we preset it here with a default value to let us know that nothing has happened. We're going to run through without any verbose output right now, and you can see in a second what the verbose output might look like. This is the event loop itself. Well, one step I should say of the event loop, for this one message, where given the user message, we're going to asynchronously use the runner and call out to the LLM using the message that was passed in, the agent that was defined to use that model, and all the instructions that we had given it. So the first thing that you'll notice is that when we call this async, we also pass in all the same information we had for creating the session. This is because you can run things, again, there could be multiple sessions going on, so you have multiple event loops running around. And asynchronously, you pass in, here's the context that I'm currently operating in. It's for this user in this session, and here's the content that's getting passed in. Go ahead and execute this once. Let the LLM do some work on this. This is inside of a for loop because this is an agentic system. So once the agent is given this message, it might do a bunch of things before actually having that final response. So the event loop here pulls out events from the asynchronous running of the agent. Every event is some update from the agent itself. As the events come in, if the verbose mode is turned on, we'll print out, here's an event that happened, here's who created that event. The initial event, of course, should be that the user message was passed in. So we should see the event author was the users themselves. And you'll see the content of the event as well. You can take a look at what's happening here in the debug statement. A bunch of things get printed out, which are helpful to understand what's going on. And then this is the key concept for keeping the event loop running for as long as you'd like it to run. Hopefully the agent will run only as much as it needs to. But as each event comes in, there's a flag that says, okay, this is the final event. I'm done processing this. The agent is done processing. If it has set this, then you know that, okay, the processing is over. You can take a look at the content and decide what the final response might be. Here we're taking a look at the content if they have some multiple parts. So if it's a non-zero array of text that had come back, we're going to take the first message back from the parts 0 here, grab the text from that, and here we're making some assumptions that the text response in the first part is actually the right one. Turn that into the final response text. Alternatively, the agent could have decided, this is my final response, and by the way, I don't have actually a response. What I've asked the runtime system to do is actually to escalate. Now here escalation ends up meaning the agent is running, knows that it's a sub-agent, and it can't handle or it can't do any more work with what's currently available. So it's basically saying, hey, escalate this to somebody else, either my parent or to some other agent that might be appropriate. In that case, the final response text that we're going to set is based on that. We're going to say that the agent has decided to escalate the current handling of the message, and that we don't have any specific message, or there's an error message, if there is one there, and return that as the final message. All that is to continue to run through one round through the event loop, instigated by a single user message, and then at the end, we'll go ahead and print out the final agent response. That's kind of a lot to go through, but keep that in your heads a little bit as you're going through all the notebooks. Internally, this is really what's happening to actually make all the machinery run. For all that work, there we go. Simple chat. Hello, I'm ABK. Hello to you, ABK. Of course, because we're going to be doing a lot of calling to agents manually, we're going to set up a helper class to actually let us do that a little bit more easily. And I'm going to call that helper class agent caller. This agent caller basically wraps up those functions that we went through each one at a time here, and also the event loop itself into one class. And if you look through the details, it is doing all the things that we'd seen above. It's saving the single user ID, the single session ID, the current agent that we're going to be running, and also the runner that's been set up. It has access to getting the session that it uses internally for actually managing stuff. And this call function here is what actually instigates one round trip through the event loop based on a user message. So it does just what we saw above, takes the user message, packages it up so that it's available as content to be processed by the agent, and then it runs through the event loop. Same kind of debug options are available as well. And this is really a stylistic choice. I'm not a native Python developer, and so this is the way I like to do things. I prefer having factory methods for things that are a little bit complex to construct. So rather than having a complex constructor inside of that class, I created a separate class that actually does the construction. And this here, this utility function, make agent caller, is what will create an instance of the agent caller. You will be passing into it all the necessary information that it has. What's the agent that you want to be running? And also, what is the initial state of that agent? Where the state is the agent's internal memory. All of this should look just like what we had run through before, but now packaged up into, here's the different elements, the major components that should be combined into the agent caller. What is the current app, the user, the session ID? Create a session service for both memory and also for managing the session itself. And then finally, also create a runner. Then having constructed all of those things, pass those into the agent caller, which wraps those all up into an execution loop. Okay, now that we have some utility functions for running an agent, we can run a conversation with the say hello agent that we created earlier. So to create a new agent caller for our hello agent, we're going to actually call out the helper function, the make agent caller, passing in the hello agent itself, and we'll just call that the hello agent caller. Then to run a conversation, we're going to have an asynchronous function that has multiple user messages that we're going to pass in to the agent caller using the call method. First, I'll say, hello, I'm ABK, and then I'll say, I am excited. We'll go ahead and run that conversation and see what that looks like. Awesome. We have created a friendly chat agent. Good work. So now that you've gotten this far, you know the basics about using Google ADK, how to create an agent, how to give that agent tools that it can use, then also how to create an execution environment for that agent. Finally, with all that in hand, you can script interactions with the agent here in the notebook, passing in user messages that let you then test out how the agent's going to work. So this fantastic agent caller class that we created, and then this construction method, the factory method called make agent caller, we're going to be using that through all the other notebooks to make it easy for once we've defined an agent, we can easily create a runtime environment using that function. So you'll get a lot of use with that. In the previous lesson, you learned how to create an agent using Google ADK, and now we're going to create multiple agents, a team of agents working together. We're going to have a root agent and then 2 sub-agents. We'll build on what we did previously where we had a say hello agent. We'll introduce a new agent that can say goodbye, and then we'll have another agent that puts them together into one multi-agent system. As usual, we'll go ahead and start with importing the libraries that we need. And then, of course, we'll go ahead and set up the LLM that we're going to use. Again, this is OpenAI. We'll define the LLM, and we'll also go ahead and do a quick sanity check by passing out a message to make sure that it's ready. Always fun to see what OpenAI might say on any given day. Usually with friendly messages, it's pretty good about saying friendly things back. Next, you can set up the agent caller. We're going to use the same class that we defined before in lesson 3, part 1. Rather than defining all that again, we're just going to import the tool that we need. If you remember from part 1, we had this helper function, make agent caller. That's going to create the agent caller class with all that it needs to run. Okay, with everything ready, you can now begin to create the multi-agent system. You're going to create multiple specialized agents, each designed for a specific capability. You'll create one agent in charge of handling greetings. That's the say hello agent we had before. The new agent is going to take charge of saying goodbye. To combine those, you're going to have what's called a root agent, and you'll hear terms like orchestrator or coordinator, top-level agent. It all really means having an agent that's going to wrap up 2 other agents and then manage their execution. That root agent is going to receive the initial user request, the hello or whatever the user decides to say, and then decide how to process that either itself or by what's called delegating, handing off to one of the sub-agents. So the root agent, this top-level orchestrator, is going to be delegating both hello and goodbye, hopefully, to the sub-agents that specialize in those tasks. Okay, let's start to assemble our multi-agent system. Again, we're going to have the say hello agent that we had before. We're going to add a say goodbye agent, and then we'll combine them together. First, we'll define the tools for our sub-agents. The first tool is the same say hello tool that we had from the previous lesson. This is the hello world function, takes in a person's name and creates a hello world message as a response. To that, we're going to include a say goodbye function. Now, this tool is going to be even simpler than the say hello because it doesn't accept any arguments whatsoever. It has a constant reply, goodbye from the cipher, no matter what you want to do. This is what you're going to get as a response saying goodbye to the user. With those 2 tools defined, we can now define some agents that will use those tools. Now we're going to have a special agent for greeting and a special agent for farewell, but you'll see it's pretty straightforward. Now, as we're defining these sub-agents, I really want to emphasize the best practices here and how important it is to have really good descriptions of each of these agents and also instructions that you're handing to them. You're going to spend most of your time, once you've set up any kind of multi-agent system, most of your time is going to be spent in actually optimizing these instructions. This is back to classic prompt engineering, and also this description. To repeat what I had said in the previous lesson, the description is what allows other agents to know what does this agent do and when should I use this agent. That's called delegation. And the instructions are for the agent itself to understand what is its purpose, what is it trying to do, and what tools does it have available and when to use them. So this is our greeting sub-agent. It's the say hello agent that has access to only the say hello tool. And then we'll add our farewell agent. The farewell agent is pretty straightforward. It's similar to the hello agent. You can look through the description here of what the instructions are. And these instructions are actually useful to take a closer look at. It seems obvious. Okay, your job as the farewell agent is to respond whenever a user says goodbye in some kind of way. Well, people say goodbye in lots of different ways. So this is a very small example of how to do some few-shot learning within the agent instructions. So here we have in parentheses some examples of like when the user uses words like bye, goodbye, thanks, bye, or see you. Those are all ways of saying goodbye. Now, most LLMs don't need this extra bit of examples, but this is a good practice to have overall, is to think, how can I help the LLM understand what this agent's purpose is and actually when to execute and what to do in its role? And of course, we're going to hand it the say goodbye tool that we defined earlier. Great. You now have two sub-agents ready to go, and now we need to combine them. We're going to do that by defining the root agent, which is going to understand both of these sub-agents and when to delegate a task to them. It's similar to doing tool calling, but the agent knows that it's talking to another agent, so the entire conversational history gets passed along, and actually control of the conversation gets passed along to the sub-agent. So it's a little bit different than tool call. But the same idea is current workflow is going to go from the agent who's in charge, here the root agent, to one of the sub-agents. So this is similar to tool calling, but let's take a careful look at how agent delegation works here. We know that the agents themselves have described what their role is, like the say hello agent versus the say goodbye agent both have some understanding about what it is they're supposed to do, and their descriptions describe to other agents what it is their job is. We're going to double down on that in the instructions that we give to the root agent. The root agent is going to be told your job is to coordinate a team of sub-agents. So you can see that in the instructions here, and that its primary goal is to be friendly. In order to be friendly, it has actually two specialized sub-agents. So we describe what those are so that the agent understands when it actually should use the sub-agents. This is like describing when you should use particular tools. The greeting agent should be used for handling simple greetings like hello or hi. And of course, the farewell agent should be used for saying goodbye, whether that's bye, see you, or anything else. And we're explicit here about saying when those messages are received from the user, go ahead and delegate to these sub-agents to actually respond to the user rather than responding directly as the coordinator. So if this works well, the coordinator shouldn't do anything other than answer general questions, and when you say hello or goodbye, it should delegate to these sub-agents for actually executing a response or generating a response to the user. This top-level coordinator doesn't have any tools to use whatsoever. It can only chat or delegate to the sub-agents. We're also going to hand it the list of sub-agents here in the sub-agents key. So the sub-agents are the greeting sub-agent and the farewell sub-agent. Now that we have a team of agents all put together into a multi-agent system, let's go ahead and interact with it. This is similar to what we did in part 1 of lesson 3, where we had an asynchronous function that managed a conversation. So here the conversation is going to be just what we did before. Hello, I'm ABK. And then later, rather than saying I'm excited, this transcript is going to say, thanks, bye. This is going to be the second user message. We've also added this true here. So if you look at the call to this agent caller, the second argument that's passed in is whether or not to be verbose in responses. We're going to turn on verbosity here so you can see all of what's going on beyond the scenes. So you can understand both the user message going in, see the delegation, see the tool calls, and also see the responses. It's a lot to walk through, but it's worth walking through at least once to get familiar with what you can see when you're debugging an agent interaction. All right, this starts off innocently enough. We get the user's message, hello, I'm ABK. And you can see that the initial event comes from the friendly agent team. So this is the top level coordinator, so the team coordinator that's going to call the sub-agents. And you can see the first action that it takes is that it wants to transfer to agent. So transfer or delegating to a sub-agent, and it's going to transfer to the greeting sub-agent. So that's perfect. In response to hello, I'm ABK, the top level coordinator realized I've got an agent who's really good at saying hello. Let me transfer control over to that agent. So the transfer of response doesn't have any value whatsoever. It's just a none. What we should see next is that the greeting sub-agent takes control. So here's another event, but now from the greeting sub-agent. And it's going to look at the transcript and see the user's message and realize that, okay, it's now my job to actually do something about this. And the greeting sub-agent is going to respond by making a tool call. You can see this function call here, and the name of the function that it wants to call is called say hello. and it's going to pass in some arguments where the one argument that's passing in is the person name is ABK. So the agent has realized that from the statement here, of course, hello, I'm ABK, it was able to extract that ABK must be the person's name, and it's going to make a function call to the tool passing in that name. And then you can see the response. Here's the function response, and the response is hello to you, ABK. Perfect. Now, the greeting subagent is done. It goes ahead and you can see that the final message is true. So that's the flag that says, I'm done processing this message. We can go ahead and terminate this particular event loop. And the final agent response ends up being the response that came back from the tool, hello to you, ABK. We send in the second query then, or message from the user, and the user says, thanks, bye. And again, the top level agent is going to go ahead, oh, actually, no, it's still in the control of the greeting subagent. So the greeting subagent itself is going to realize, okay, this is not something I should use. Please transfer this to the farewell subagent. So it's aware of the other agents that are available, transfers to the farewell subagent, and that is the end of that function response. Here you can see then a message from the farewell subagent itself. It again is going to look at the transcript now that it's been given control of the current conversation. The first thing it's going to do is realize, okay, the user said goodbye. Let me go ahead and call the say goodbye tool to figure out how to respond to them. And so here's the function call to say goodbye. And of course, it takes no arguments as expected. But the response to it is the constant that we saw earlier in the tool definition. It's going to get a farewell that is goodbye from Cypher. And that again is the final response for this event loop. And so that is going to be the final agent response, goodbye from Cypher. Okay, that was a lot to walk through. It's worth taking the time to do that for anything else we do in these notebooks. You can really see all of the interactions about tool calls, agent delegation, and also the responses and the changes in state overall. So really useful to do. We're not going to do that for every notebook, but if you'd like to on your own time, please do take the time to really understand what's happening behind the scenes, because what's happening behind the scenes is going to affect, of course, how you do the overall agent definitions and also the agent orchestration. You're going to take one more step in this multi-agent system. We have an execution environment for agents. We've got a team of multiple agents that can work together. They can delegate tasks to each other. And then each of those agents also has tools that they can use. The last important component for all agent systems is having memory. Memory is just internal state happening for a particular session across any agents that are involved in that session. And of course, the user themselves. What is session state really? Session state in Google ADK by default is really just a dictionary that's available that you can update keys within that dictionary. And when you update values of those keys, Google ADK tracks those changes. It tracks deltas to the state, basically, and updates the overall session state to keep it consistent across all agents, whether they're running in parallel or running sequentially. Because it's an asynchronous system at its heart, it manages all the state updates. Agents have a few different ways of interacting with state. One way, the way that I prefer in the primary method for interacting with state, is through the tool context. So whenever a tool is called, there's an extra parameter that's available that is the context within which that tool has been called. Given that tool context, the tool itself then has access to the current state or the current memory of the agent, and it can use that memory for actually making either different decisions, creating different output, whatever is appropriate for the memory. The other way that agents can interact with state is by using an output key. So rather than using a tool call for updating some memory or for accessing memory, you can take the actual output from an agent, that final response, and rather than just turning that back as the response from the agent, you can save that into state by defining an output key. So when you see this final true, the message related to the final true, here it'll be the text goodbye from Cypher, could get used for updating state itself. That's very convenient sometimes, and we'll do a little bit of that later on in some of these notebooks. Okay, in this next step, we're going to set up some memory. We always have the in-memory session that we're using right now. So the memory is saved just within RAM that's not being persisted to a database. Of course, that's the best thing to do for a production system, but for convenience, having in-memory state is perfectly fine. We're going to update both of our tools to actually take advantage of using that in-memory state. So both for say hello and say goodbye, we're going to update those tools to take advantage of the tool context to update session state or memory. You should do this one at a time and take a careful look at the differences here. You'll notice that we're importing tool context from Google ADK. Tool context is the class that takes care of keeping track of the session state in addition to other things that is useful for tools to have access to. So we're going to update the sayHello function to be sayHello stateful. It still accepts an argument for the user's name, but it now has this extra argument called tool context. It's the tool context that's going to let us get access to the tool context passed in for the session by the execution environment. So in the tool context, there's this state dictionary, and we're just going to update the username key, and the name that was passed into the function we're going to use for updating the session memory or the session state for the username key. So this is pretty straightforward. Username. Now we have a dictionary that is shared across all agents and across all tools that will have that value that was passed into this function. This is a way of sort of keeping track of things by natural use of functions and also then preserving them for later use. For debugging purposes, when this tool is called, we'll go ahead and print out the update to the session state, particularly to the username key. And then, of course, we'll do what we had done in the previous sayHello. We'll send a query off to Neo4j using a query parameter that is the username. So let's go ahead and define that. Now that you've defined that, you can define the same thing for the say goodbye. And again, as you're defining this is just an update to the say goodbye that we had before. Now the difference is that this say goodbye, even though it doesn't take an argument for anything related to the person, it has no custom arguments here, it does get this tool context passed in. And I should mention that this is something that Google ADK does automatically. When it sees a tool where the last argument to the tool is tool context, it automatically injects that to the tool call. So when say goodbye stateful is called here, it's going to get tool context, but nothing else. But because sayHello stateful has set the state, the username into the state, say goodbye can actually access the username. So now we've remembered what the user's name is. We can access the state for the state key username and then have a default value in case the user didn't identify themselves. But we can get from the dictionary the username or default, assign that to the username, and then use that for actually generating a goodbye statement. You can then define a new stateful agent for farewell. And again, that's going to be the same as we had as the previous farewell agent, but now it's going to be called the say goodbye stateful tool. As before, you can combine those into a multi-agent system by having a root level agent or a coordinator agent that's going to use both of those as sub-agents. And this is exactly the same as the other root agent that we had, but now it's just using all the sub-agents that have ultimately down at their core these tools that are stateful based. You now have a multi-agent system that takes advantage of memory. You can give it a try. You will use our friend, the make agent caller, passing in that new root agent stateful that is the top level coordinator, create a caller for that. And to see the change in the session, we'll go ahead and get the session directly from the caller. Remember, there was a utility function for getting that if you look back at the agent caller class. We'll go ahead and get the session, and then based on that session, we'll print out the initial state when this is created. And we should see that there's nothing in the current state. As expected, the initial state is empty. You can now define a conversation. It's the same conversation we've been having. Say hello, say goodbye, and let's see what happens. Actually, I'm going to take out these verbose statements right now, and you can decide to keep those in or add them if you'd like. Run it either way. But just to keep the output to a minimum, we'll go ahead and run this without the debugging statements. And what's really important here is that we saw that the initial state was empty, and we expect that once these calls are done, the initial state should turn into a final state. Here we're going to get it again, and that the final state should actually have the user's name as defined by the call to say hello. Awesome. So our utility functions printed out this update to the username here. And we also see when we get the session and then get the state from that session that the final state includes the username ABK. Fantastic. Everything's working as expected. Now, if you'd like to, you can actually run this in an interactive environment, even within this notebook. you can set up a small helper function that's going to have a loop for getting messages from the user and then just calling our caller, passing in that message. This will run as long as the user doesn't pass in a message that says exit. When you set that up and then run it, you'll see a little box appear. So when you run the interactive session, you can type in a message and just see what happens. And I'll start by not revealing my name, see what happens. Okay, that's kind of funny. So the LLM decided that my name is there based on this message. That's not really great. Let's correct it. Let's say, and you can see just by passing in my name is ABK that the tool context actually updated with ABK. So there's a tool call still to say hello to ABK. And because of that, the LLM correctly identified my name is ABK, save that into memory. This is fantastic. If I say goodbye again, we should now get a nice message by ABK as before. Give this a try, interact with it, and see what you can come up with. And of course, if you'd like to, change any of the code and see what the impact is of that. Okay, you've gotten all the way to the end of lesson 3. You've created a basic agent that is a single agent that says hello. And then you created a multi-agent system with 2 sub-agents specialized in saying hello or saying goodbye, and then a root agent that coordinates their interactions with the user. With this in hand, you're ready to continue into actually doing agentic knowledge graph construction. In this course, you learned how to build a multi-agent system that transforms your structured and unstructured data into a knowledge graph. You learned how to set up each specialized agent in your system, what prompt to use and what tools to define, and how to share context among the agents. Congratulations on completing this course, and I'm looking forward to seeing what you'll build on your own.